Hello everyone and welcome back to Network 13. Today we're going to be doing an experiment with, and let me get a close-up of it for you. There we go. We're going to be doing an experiment with this, which is a Hitachi HM6116 2K static RAM. Okay, first of all, some background on this. This was designed and manufactured by Hitachi of Japan, and as far as I can tell, sometime in the early 1980s, although it may predate that even a little bit. This is a CMOS static RAM. It has 2048 memory locations, or words, and each memory location holds 8 bits of data. And this comes in a 600 mil plastic dip package, so this is really kind of old school stuff here, kind of Stone Age. Now, some notable uses of this that I found today were, this was used in the Commodore VIC-20 computer, one of my favorites, my very first computer that I ever owned. It was also used in the Commodore 1541 floppy drives, and it was used by Sharp for a few of their pocket computer models, PC 1401, PC 1245, PC 1251. Also used by Texas Instruments in their compact computer, the CC40. And it was also used in, I believe, by Bally and one other manufacturer. They used it for pinball machines and some old classic arcade games. Cabinet games you'd find in your local video arcade back in the 80s. All right, very quickly, just going to look at the data sheet. This is runs off a 5-volt supply, and the inputs and outputs are TTL compatible. TTL levels, of course, anything above 2 volts is a high, and anything below 0.8 volts, I believe, is a low. And this also came in a 24 lead SOP, a surface mount package. Here's a block diagram, and we have 11 address lines, so that's 0 through 7 and 8 through 10 here. We have 8 data lines, or I/O lines, I/O 1 through I/O 8, and we have 3 control lines, which are output enable not, write enable not, and chip select not, and I'll explain what these are a little later. And this was a kind of a muddy copy that I got off the web, so I had to fill some of these in because I couldn't really read from my print. And just to go a little deeper into this, it's typical datasheet stuff here, and most of you are probably familiar with this anyway, but you have different timing diagrams. So if you were reading data or writing data and you need certain amounts of setup time on your address lines and certain amounts of wait time after you've enabled your output or selected. And that's just kind of shows you how to do your setups without having any data collisions. Now this really isn't going to apply to what we're doing today because I'm doing this stuff manually. What we're doing is much simpler than this. But if you're connected this to a microprocessor in a design, this would be very important. You'd have to make sure all your setup times and things were correct. And of course, there's a lot of good information in these data sheets. A lot of good notes, and I will be providing a link to this data sheet, or actually a little cleaner copy of this, in the section below the video on the YouTube page. And I'll also be providing a data sheet to the other IC we're using today, which I haven't talked about yet, which is let me see what it is. Okay, the other IC we're using today, it's a 74HC244, which is an octal buffer with tri-state outputs. I'll provide a link to that also, but that's not a terribly complicated IC, so it'll be pretty obvious how it works and what it's doing when I show you the schematic for the circuit in a moment. Okay, this is our circuit today. And here's the HM6116, the static RAM. This is the 74HC244, which is the octal buffer. And we'll start at this side. These are our 11 address lines, and we're only concerned today with the first 4 because we're only going to be addressing the first 16 locations in the static RAM. So the rest of the address lines we just tie to ground, because they're going to be low. There's a write enable signal, which I have connected to a push button momentary. I also have a capacitor across it to debounce it a little bit, though I don't know if that's really necessary in this case, but I did it anyway. And I have an output enable going to a switch. And if you look at, these are all at pull-up resistors. So when the switch is open, the line will be high. When you close the switch, the line will be low. If we move over, oh, by the way, so and this is our address switch set. Over on this side, these are our I/O lines, or our data bus. We have another bank of switches, 8 switches here. These all also have pull-up resistors. Once again, if the switch is open, the line will be high. If the switch is closed, the line will be low. And we're using the 74HC244 buffer here to provide high Z on this side to our I/O lines. And we're using the outputs of these to drive our LEDs. So we have an LED, actually I can show you. We have an LED display here. And we're using 8 of these LEDs. There are 10 in this package, just to show what data is on the data bus. Okay, so earlier I talked about timing, signal timing, and this does become important even in this experiment. So I cannot enable my output while any of my data lines are low. I risk damaging my outputs if I do that. So in order to enable output, I have to make sure all of my data lines are high, which means all these switches have to be open. So I just have to remember to do that when I'm doing the demo in a moment. And the other piece I had to tell you about was, here on the 74HC244, there are 2 output enable lines here as well. This IC can actually tri-state output also, so if your output enable were high, these would all be high Z. Now, I think normal application you'd be using this side to drive a bus, but I'm using it a little differently here. I'm just using it to drive my LEDs. So I'm probably not using it in the original spirit of what it was intended for. But in our case here, we tie output enable for both sections low because we want the outputs to stay on. We don't want them to tri-state. Just very briefly, we'll go through the different cycles here. So the write cycle will be as follows. I'll set an address, and I'll set whatever data I want to put in that address, and I will press the write enable button, which would be pulling the write enable line low. And then if I want to read the data, I will set the address, the location that I want to read. I will make sure all the data lines are high, or all the switches are open, and then I will pull output enable low, and then we will see whatever's in the memory location on the LED display. Okay, so this is our circuit all wired up and powered up, and a brief explanation of what we're looking at. These are the address lines, or address switches, A0 to A3. These are our data switches, which are D0 to D7. This switch here is the output enable switch, and the push button is write enable. So right now we're reading all highs. If I pull output enable low, we can see what's actually on some of these, what's in some of these locations, which they may just all be high, I don't know, but let's see if we switch through some of them. So this would be location 1, which has just some random stuff in it. This would be location 2, has some more random stuff, location 3, so on and so forth. But what we want to do is we want to write some data into this. Okay, we're going to try writing some data into some locations. So we're going to start with location 0, which are all lows on the address lines. And we're going to write, let's see, we'll write a 1 into location 0. And the way we do that is we pull right enable low with the push button. Okay, so location 0 should have a 1. And I realize this is a bit tedious to watch, perhaps. But this is just an experiment, just a demo. You wouldn't be doing this by hand unless you were crazy. Now we have location 1, and we want to write a 2 into that. So we write enable. This is location 2. We want to write a 3 into that. Write enable. And then location 3, we want to write a 4 into. Write enable. Now, like I said before we can enable the outputs, we have to make sure all of our switches are open. That's important. Otherwise, we can damage our SRAM outputs. So we'll go back to address 0, and we'll put output enable low. So address 0 has a 1. Okay, that's right. Address 1 has a 2. Address 2 has a 3. See? And address 3 has a 4. So what we were able to do is we were able to write these values into the SRAM and read them back, which is what it's supposed to do. Forgive me. Okay, we can do something different. Well, if we went to location 15 and we wrote, let's see, we want to write something identifiable. So maybe we want to write an 8 to location 15. Or a 9. Let's write a 9 to location 15. So we do write enable, location 15, and then we set all of our data lines high again, and we write enable, and there's our 9. So there you go. I mean, it's not very glamorous, but I think this shows the basic principle of address and data, address bus, data bus, and display on your data bus. Okay, very good, very good. I hope to use this static RAM in a little more sophisticated experiment in the future where I'm able to write and read from it using a microcontroller, maybe an Arduino board or maybe a PIC, I don't know, something a little more sophisticated than this. Okay, that's it for our video today. If you have any questions or comments, feel free to leave them in the comments section of the video. You can also write to me at network13.contact@gmail.com, our email address. Feel free to like this video if you liked it, or give it a thumbs up, or give it a thumbs down if you didn't like it. You know, any kind of criticism is welcome as long as it's not rude or hateful, I suppose. And with that, I will say, as always, thank you for watching.